So now, having seen all those 4 functions, now it's time to get into the whole process, run the whole process. Let's look at the code for doing this. So we start an outer loop or iterative loop which ranges to the number of bandits which we have. So we, as we said, we have 2000 different bandits. So we are the first outer loop is for the complete number of bandits. So we initialize all those values, as we said, the calibrated value and the QTA values and the arm selected count for each bandit. We initialize this for each bandit. Epsilon value, we just keep it as constant. It doesn't change much. But we initialize all the other the trackers for each bandit. Now for each bandit, then the next inner loop goes into the complete number of steps. So we have, as we have defined, we have earlier defined the 10,000 steps for this. So each bandit will run for 10,000 steps or 10,000 pulls of different levers to get the range. So the first is to select which action is the best action. Select your action using the my action function, and then using that action, get an indicator whether that was an optimal pull and what was the reward which was generated out of it using that optimal action reward function. And then we update based on the rewards which we get and the optimal pull. We update the arms select count and also the value for that particular action, which is that which is based on our that formula, that is new estimate is old estimate plus 1 by step size into reward minus the old value. So that update also happens, and then we store the rewards also in the tracker which we have, and the optimal selection, whether it is optimal pull or not, that also we store. And finally, now we the next step is to calibrate or get the non-stationary reward function going, wherein we increment the reward function using the function calibrated arm. So that's the whole process. So it runs for all the 10,000 steps for a particular bandit and for all the 20,000 steps. So it will run for some time. We will pause for now, and then once the run is completed, maybe we'll see what the outcome is. So now we have completed the complete iteration, which is, and now what we will do is we will average the rewards based on the number of bandits. That is, and now as you know, the reward shape is it is a 3-dimensional matrix. With the first one is about the number of solutions we have. We are running only the first solution right now. The next dimension is for the number of bandits, and the last dimension is for the number of steps. So what we will do is, since this is a simple averaging method, we have stored it in the first index, that is 0 index. So we'll take the 0 index. So now we'll have the matrix as 2000 into 10,000 in a kind of matrix, because 2000 number of bandits, 2000 bandits, and for each bandit 10,000 steps. So what we'll do is we'll average this across the different bandits. So ultimately we'll have a matrix of just 10,000 steps for the 10,000 steps which we have done. What is the kind of average reward which we get? So that's the shape. That's what we're going to observe, and let's plot this in using matplotlib. So from the plot you can see how the average reward increases in value with the amount of steps. So this is the learning process which is happening. That is, the average reward which we get kind of increases with each step. So that's the effect of exploitations and exploration and exploitations of the arm, which gives the best reward. Now let's also look at which of these arms are giving the best kind of reward. So you can see the sixth one, which is here. I mean, it could be different for you, but for me it is, because it's a stochastic process. So here you can see this is the sixth one is the one with the maximum value, and you can see that the count is also the highest for that sixth arm, which means that this has been exploited the most. And obviously, because this is the best value, best kind of rewards is generated by this, and it's been exploited the most. Let's also kind of look at whether this particular solution gives you the best optimal actions. Is this the best optimal actions? Now you can see from the graph, this is the graph of the kind of optimal actions, whether the optimality of those actions. Now we can see the optimal actions were got only for 40% of the time. So this particular solution, which is a simple weighted averaging method, gave you only an optimal action for 40% of the time. So maybe so this is obviously a very simple method, which is a simple averaging method. Maybe what we will do is we'll try out a different method also, weighted averaging method, and most of the steps are the same, maybe with one or two simple differences, and then we'll see how many of these plots go, how is the reward function, and how is the optimal action plot, how is it going for this method also. Now coming to the weighted averaging method, so let's recap of what is the simple averaging method. So simple averaging method, you have a step size of 1 by n, which is the number of times that arm has been pulled. That is your step size. But the only difference in weighted averaging method is, instead of the 1 by n, that is taking a reciprocal of the number of times a particular arm has been pulled, we use another hyperparameter called alpha as a step size. So that's the only difference between in a weighted averaging method. And alpha values we usually select between 0.1 to 0.01. Any of these values we select for alpha value. So let's look at the implementation of a weighted averaging method too. Now the weighted averaging method has because of the weighted averaging method, we need to make changes to just one of the functions. So here the update mental model, that is how do you make your update, that's the function which actually changes. So here you can see we have replaced that step size by a parameter called alpha, and alpha we have defined as 0.1. One more subtle change which we can notice is, since we don't divide it by the number of times, or the step size is not reciprocal of the number of times a particular action is pulled, we don't have to track that number of times an action is pulled. So that initialization also is missing, would be missing from our loop. So that's and otherwise pretty much it's the same kind of process. So let's run this and then see the values, the reward values, and what kind of results we get out of it. So now we have got the results of the weighted averaging method, and we'll find the average rewards. Now you can see the rewards is for index 1, index 0 was for the simple averaging method, and index 1 is for the weighted averaging method. And you can see now the average reward has actually increased. The value of the average reward has actually increased than the simple averaging method. And you can also see the optimality count. Now even the optimal actions, we have an optimal action for almost 80% of the time. Earlier you found that in simple averaging method you had an optimal action only for around 40% of the time. Now it is almost 80% of the time, which indicates that weighted averaging is actually better than the simple averaging method. Now so this takes us to the end of this particular exercise. So this exercise was only to give you a feel of what is involved in the in an action bandit, and how you can build solution. Now there are different types of other solutions for action bandits, like upper confidence bound and so many other things, which we will maybe discuss in a later post. Now what we will do is we'll take these key steps or some of these key elements of an action bandit, and in the next post what we will do is we'll use it to build our prototype for self-learning recommendation systems. So as a final wrap up, let's try to connect the bandit problem with the recommendation systems, and how do you make that parallels between both of them. Now the different products which is being recommended for a user is like your lever, okay, like the arms which you are pulling. Now each arms has got a certain kind of value. Now the success of your recommended systems, or the objective of your recommended system, is to understand what kind of products best appeal to the user, or for a specific user which lever or which product to be recommended, or which type of product to be recommended, so that there is a higher chances of the user buying that. Now the self-learning part is when you kind of recommend the products, and the user obviously has the option to either, three different types of actions can be possible by the user. One is the based on the recommendations, the user can ignore the product, it can buy the product, or so on all these things you can either ignore the product, buy the product, or even click the product, browse the product, etc. So these are three different actions which is possible. Now let's look at these this specific figure. So three products have been recommended. Two of them were ignored and one has been bought. So the product which has been bought will have a positive reward, and the others will have a negative reward. So based on the reward function, we update that the arms or the different levers which has been pulled, and this is how the parallels to the bandit problems is for the recommendation system. So this is what we will implement in our next post, which is on building your prototype using Jupyter notebooks. We'll build this recommendation systems in the next post.